Hello, am I audible? Please let me know once. Then we can start. You can write it in the chat box. Yes or no. That's also fine. I think it's visible. So we'll wait for 2-3 minutes and then we can start today's session. So let's begin with this discussion. And so this week, mostly the parts that were covered were related to the protection part and how the microgrid protection, and after the islanding is formed, the islands are formed or localized, then how the protection schemes needs to be designed or modernized so as to uh, deliver a better or much more adaptive protection schemes that can be developed so that the the smart grids or smart distribution grids can be protected from various kinds of faults and all these things. So these this week's part were mostly covered the topics like the protection, where protection schemes, how the adaptive relays needs to be developed. It's a basic say, conclusive overview, so that after that we'll discuss it one by one. And the major thing or major proportion of this week's lecture covered the protection part as well as the how the microgrids or control strategies, or sorry, the modeling strategies needs to be formulated, the equipment modeling, and how the AC microgrids are to be modeled so that they can handle the modern day challenging scenarios where the problems like the grid connected mode or grid or the islanded mode of operation can be easily operated. So for that, firstly, the adaptive protection schemes, why these schemes needs to be developed, that is also one thing we need to uh, take into consideration, because we have the synchronous based D or synchronous operators, synchronous generators, and all these synchronous generators can deliver the. Okay. So how these synchronous machines can develop or deliver the required amount of power, but with the microgrids in place and with the modern uh, distribution grids in place, how these things needs to be modernized, because for the, as we all know that for relays we have already. Yes. So for relays, as we all know, we have some set point values. Okay. So based on this set point value, like we have a threshold, and if this threshold is crossed by the current, or means the based on the sensing uh, current, if this threshold crosses this limit, then the threshold is crossed by the fault current. So in those cases, what we can see is that the relay would send a command to the circuit breaker, and the circuit breaker would trip that faulty location, right? And also that too in a within a prescribed time frame. So we have some time constraints, like we have some time constraints that can be considered for the primary as well as the backup protection. So these things will take up one by one and we can discuss them. So, and also in these modern day smart grids, the issue is that we can we we already have a prescribed limit, okay, for these relays, but in the due to the changing dynamics for the renewables, Okay, due to this changing dynamics, some renewables can be solar or wind based. Okay, so using this for the solar and wind based renewables, now they are injecting power to the grid, and that is in a the major issue lies in the uncertainty associated with them. Okay, so due to this uncertainty, we do not have the exact, or the forecasts are highly uncertain. So we don't have the exact values that these things can be controlled. They are uncontrolled. So the net fault current, which is let's suppose the fault current which is previously, if the fault current that was being faced by these relays was, if let's suppose it was around, if it is 5 PEU. So these were the set values for the synchronous based DERs. But within the DERs itself, though we know that these things are likely to change, but based on the scenarios. So since these fault currents do varies, because let's suppose we have a bus here, okay, and from here we have a synchronous generator injecting, and from here we have a PV injecting, right? So we have lines. Let's consider transmission lines. Anything. So what we can see is that we have, and if we can to be present, consider them to be present here if a third bus, if we can consider a third bus, then the problem becomes much more tough. Okay. So suppose here we have loads. So here we have breakers in place in these positions, which are operated by the switch sensors. Means they have the relays which senses the fault currents, and based on that they send the trip command to these uh, breakers. So the problem here becomes, suppose here the fault current which was previously, let's say for IF1, due to this, for the time being, let's forget that we have the PV here, PV generating plant here. We let's consider that omit this case. So if considering this case only the synchronous generator in place, if the fault current, if suppose a fault occurs here, and the fault current that passed through this uh, faulty fault location is IF1 from this side, there would be another fault current which would also move on from this side. So the issue is that now with the PV in place, with the PV in place, these two fault currents, the magnitude of these fault currents would change, right? The magnitude of this fault current, because this would also inject a fault current to this fault location, and similarly this path would also face at some different fault current. So ultimately there is a change in the magnitude of the fault current. Okay, so now this relay, let's suppose the breakers, here we have breakers, for the breakers we have relays R1 R2. So these relays would send different fault currents, and accordingly they would send trip command. Sometimes the problem might arise that the trip command that is faced by these Sometimes there may be case where the trip command which is given by the relay, if the threshold is not crossed, so in those cases the relay won't send the trip command, and accordingly the circuit breaker won't operate and fault would persist. So the to 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 address these kind of challenges, or to encounter, or to make, or to develop something, some different mechanisms can help out in mitigating this kind of problems or issues that we face in the grid protection. And mostly these are the related, this is the case for the transmission side, so similar goes for the case for the distribution side. Let's just consider the similar scheme where we have a substation. From the substation and the distribution, which is mostly radial in nature, distribution line, and we have the buses here. Let's consider 2 3 buses, and we have the loads here. Okay, so, and this would have been well synchronized, but the problem lies that we are nowadays we are placing the PVs in the grid, distribution grid itself. Okay, so now if a fault occurs here, so the magnitude of fault current would also change here. If a fault occurs here, the magnitude of fault current would that would be faced by this from this substation. Let's consider this as a 33 by 11 kV substation. So this fault current that was previously prevailing here would change, and mostly the distribution side was radial, but nowadays it has become also weakly meshed systems. So the problem would become much more difficult. Okay, so the contribution of fault current would change, and that would lead to something uh, problematic, and that would definitely cause the relay settings to sometimes it might not surpass the threshold value, because if it becomes in the opposing direction, and that in those cases the fault magnitude might be different, and that might lead to maloperation of these relays. And for that we need to design adaptive protection scheme. So, and also for other case, that the primary protection scheme and the secondary backup protection scheme, we have some prescribed time setting, that after or before this time setting only, prior to this time setting only relay 1 would operate, and post that time only relay 2 would operate. Or post that time would, that on time would definitely come in picture when that relay 1 won't operate, because in ideal scenarios it should operate, but practical scenarios things might change, and things might uh, encounter some different problems, and that might lead to maloperation or non-operation. So there has to be some backup protection scheme. So these are mainly the topics under discussion for the uh, protection approaches, where the distribution or smart grid protection approaches. So one of those approaches is to, so as I have discussed, that first there are stages which we have gone through. I think that 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 is also known as protection coordination. So in protection coordination, so based on the positive sequence component, based pre-fault case and post-fault case. So first relay 1, for all these things, relay 1 is being the time of operation for relay 1, the setting of this relay 1 should be uh, priorly determined. Okay, and after that relay 2 which is also the backup relay for this relay 1. Based on the time, it should be given some specific time, like uh, relay 1 would be having some time. Let's have let's it have some time of operation. Okay, so the time of relay operation means the relay setting, and after that the circuit breaker operation time. So these two times should be given prior for the relay 2 to operate, because that amount of time it should be uh, it is required by relay 1. So that kind of time should be given, that amount of time should be given to relay 1, and after that only relay 2 would actuate based on the setting value, because there is also called the zone of protection. So zone 1 protection, zone 2 protection. So so here, based on the positive positive sequence based current based adaptive protection scheme selects. Suppose here we have a fault F1. Okay, so based on the fault on F1, there can be cases where this DG as well as this DG would also participate in this fault. So if if that our main aim now is to disconnect these two sections. Okay, so disconnect these two sections, these two relays should operate to disconnect this section. But if sometimes if it can't operate, then we'll have to go for backup protection schemes. So again, once it is relay, once these relays operates, then this section becomes the islanded. This section gets disconnected from the main grid. Okay, and now the system becomes islanded, and islanded microgrid with the DGs in place. They can uh, the take care. They will have to take care of this islanded portion, because the grid is also already disconnected, right? So for that we have some setting values that we have already seen in the slide. So I'm not going through these values or writing those equations again. Okay, so here what we can observe is that now in the distribution side, first here we have the voltage reference, and based on that, when it was a healthy running condition. So let me first draw the line or draw the picture of the fault before and after the fault, because this VE and VE already you have seen, I think. This is from the DER side, and here we have observed a okay, loads are present. So here it is VE, and here it is VH, and here we have ZH, ZGH, Z Z1GH, Z1EH, and Z1E. Okay, so and here it is loads, load current, positive sequence. One means positive sequence. So you can observe that these phasor. So based on these operating conditions, the phasors were VE with V1 pre. Okay, since in the distribution side, as already stated, that in the distribution side, the phase angle between the voltage magnitude and the currents are quite low due to the smaller Yes, due to the smaller amount of what to say, huh, the angle become an angle between these two is very low. So for the fault conditions, what we can see is that in case of fault, we need to find out the superimposed component. Okay, so superimposed current components we need to find out. So for a fault here in uh, one is, this is the diagram for this one. Here we have a DER, here we have the grid. Okay, so here we have F1, here we have F2. So which relays should operate or not, that we need to find out. So based on this, if we see that if fault occurs in F1 position, so this amount of fault current would flow. Now this amount of fault current would result in this much amount of, this is the resultant value. So this much amount when gets sorry. So this much amount of fault current, this is the resultant of these two vectors. So it is directly replicating this value. Okay, del f I1, del sorry 1 f1. Okay, if1. So 1 f1, that's positive sequence, superimposed component. So based on this, we can find out that this is the fault current for this position. Now here comes the, now here, and also phi f1 becomes the angle, right? So when this is the magnitude, this is the angle. So we need to find out two systems, like two things, that one is the over current, whether it has crossed the threshold or not. Threshold is crossed greater than over current, whether it has flown or threshold is violated or not. And the other thing is that we need to find out the phase angle, and based on that phase angle we can say whether the direction, what is the direction, because two things we need to find out: the directional component, we need to, is the direction of the, we relays have two parts. The one is the directional component, and uh, one is the overcurrent component. So overcurrent component, that we can find out from the magnitude, but the directional component, so we need to find out that directional component, that whether the fault has occurred in the front end side or the leeward side, front side, leeward side. So accordingly, though that relay would operate, because, and whether that relay would be a backup relay, because we need to pinpoint that exact location, right? And to find out or to pinpoint that exact location and treat that exactly that point, we need to properly find out which direction, means the find out the direction, and based on the direction value we can detect that which side relay should operate. So that we can find out from the phi f1 for phi angle, for the phi angle, and if fault angle is 2, then it is phi f2 we can find out, and accordingly if it is positive, then we can already say that the fault is on the positive, if on the front side or back side, based on these values, that is phi 1 and phi 2. Okay, also there are some equations, so superimposed adaptive protection schemes. So that positive and negative sign, that is the decision making component. So we need to find out whether the fault has occurred on the positive side. Based on that, will have the +1 -1, that will have the value that for upstream values, if the fault has occurred on the upstream side or downstream side. Okay, so with the phi value as a negative value and upstream side we can see the decision should be -1. Okay, and similarly we can see them directly, so I'm not emphasizing them now. So mainly we'll have to design an adaptive protection scheme where the you can directly refer to the rule base. Okay, rule base for the adaptive protection scheme. So there you can get that the uh, magnitude and direction, which direction should be considered for which purpose or not, means whether the front side based on this value, whether it is positive or negative, we can detect that which the fault is on which side. Now this was the case for one of the techniques, but of the we'll have to check whether the adaptive, whether we are doing the adaptive protection or we are designing adaptive protection schemes, right? So these adaptive protection schemes, so we have some problem like synchronous based DERs. They impose fault current of 5 unit per unit, but whereas the inverter based DERs, they impose fault current of around approximately around 2 per unit. So there's a certain mismatch amongst them itself, right? So to handle or to take care of these two mismatches, we need to scale them down. So before that, uh, the the decision that was previously given uh, by the by both the units, that has to be merged. Okay, so that merged application, we can see that if we put the overcurrent and the directional, okay, overcurrent and directional together in an AND gate, okay, and in this, out of this AND gate, if both of them becomes 1 and 1, logic becomes 1, then only we'll have 1. Otherwise uh, the thing won't operate. Okay, so both overcurrent relay as well as the directional relay has to send the trip command, has to send the signal, so that, so first there are stages that firstly we'll have to identify the fault type and as well as the section of the fault location. Okay, then we'll have to calculate TDS, time setting. Okay, and if this based on this, we'll have to, based on, we can find out that the trip time, whether the relay the overcurrent value is threshold is passed, and which scheme would be now operating based on the time that primary scheme would operate or the backup scheme would operate. So we can get based on the time, we can actuate those quantities, those equipments, that whether now the time has elapsed, so the backup protection should come in picture. So on the other hand side, we'll also have to calculate the positive sequence components, positive current components, so positive sequence superimposed current component. Okay, and also we'll have to compute the angle, because based on that angle we can say whether in which direction the fault is occurred, on the front hand side or the backward side. So because which relay should be the primary protection, which relay should be a part of the primary protection scheme, and which relays should be the part of the backup protection scheme, that also we need to identify. So after that we'll have the rule base. So accordingly, the decision one or these two decision from the overcurrent and directional would actuate in the AND gate, and the based on that output, that side relay would trip, means the decision is being finally given, and accordingly the relays would operate. So the setting value means the time of operation, the relays should be operating, and accordingly we'll have to find out that the set point value would be from zero point 0.3 to zero point 0.5, and within this time they are operating. We always have to take into calculation that CTI, this CTI value should be less than this zero point 0.3 to zero point 0.5, means within zero point 0.3 to zero point 0.5. If it is following this, that is there are some rules that for the grid codes that they should always be a part of these values. So accordingly they can play. So we can play. Sorry, we can play with the design part. Okay, so here's the adaptive technique. If fault can be seen in the relay by the contribution of IBDERs, then that is IBDERs is the inverter based DERs. Then the fault value would be, then the del of IF would be calculated, and after that, if it is here you can see the plus and here we can see minus, right? So for the synchronous based we have the minus here, so that here with the numerator becomes small, so accordingly del if for this case would become less. Okay, so for IBDERs, fault current 1 and fault current 2, based on this fault current 1 and fault current 2, del f would be multiplied so as to find out the IF, that is the fault current participation by that DER. Okay, so we can also find some hardware tests were already done, and based on those hardware tests we can already see that the superimposed, this is the superimposed adaptive sequence current based protection scheme, and we can see that that the protection scheme that is being designed is both based on the overcurrent part as well as the directional part. Again, this is for the superimposed negative sequence component. Okay, so here we are mostly emphasizing on I2, that is all these phase angle and this all this phase angle and the phase angle and the fault currents that are calculated. These are the means these are the primary, means the steady state condition, and after the fault these are the fault currents. So accordingly we need to calculate the delta I2F1, and we can find out these are the superimposed negative sequence component. Okay, so based on the superimposed negative sequence component, the logic remains same. We'll have to design the impact factor, means we can, these are the impact factors, so we can calculate them. Okay, so these are, we can calculate the impact factor, and after calculating the impact factor what we can do is that we can compute the relay fault current, because once we find the impact factor, this is the impact factor, so we can find out mathematically what is the relay fault current. And once we calculate the relay fault current, now we'll have to emphasize on the negative part, is the negative sequence part, so that we can find out the phase angle. Okay, so to calculate the phase angle, we can, what we can do is that the negative sequence components needs to be calculated, and based on them we can find out the fault currents negative sequence, and accordingly we can find out the phi. The phi is needed to calculate the direction, to find out the direction. Okay, and direction is needed because to see, applying the rule base, it is needed to find out whether the fault has occurred in the front end on the outside or the back end. Okay, so some discussions were given and some results based on hardware results were also discussed, so that protection scheme based on these superimposed positive and negative sequence based protection schemes, and accordingly how the relays should be designed, these things were being discussed. Okay, so related questions you can ask. Okay, so otherwise we will be discussing about the modeling of the storage devices and why these storage devices are required. Okay, because this is the adaptive protection schemes are becoming predominant nowadays, so that's our aim. We also need to design the protective equipments to deliver the best possible results. Okay. So next we can discuss the storage, importance of the storage. So already we have previously seen the importance of why the battery energy storage systems are being deployed nowadays, because uh, already we have these thermal power plants, hydro power plants, all these things are in place, but with the aim of developing smart grids. The main aim of developing smart grid is to develop the or to maintain the continuity of the power supply. That's our aim. So that aim can be fulfilled if we have ample amount of storage to suffice that need. Okay. Now we presently we have two peaks. We generally face a morning peak and an evening peak. Okay. So in today's Indian context, we face two morning peak as well as the evening peak. But our aim is to minimize those peak, and there's a valley also in the mean of between the in during the afternoon, and we face a valley. So what we can do is to our aim is to make the power consumption profile flat, and if we can make the power consumption profile flat, then the system adversities number of systems to be switched on or off, that we can control. Okay. So what we can do is that we can calculate the amount of storage required to suffice that amount of energy which is in between these two peaks. Okay. So we can accordingly we can place battery storage systems or pump storage systems. Already the usability of the pump storage systems we have already discussed, that the usability of the pump storage systems where there's an upper dam and a lower dam, and from this upper dam or lower dam we during the peak hours we switch on the pumped hydropower plants, and during the off-peak times we just pump the water that is stored in the lower dam to the upper dam, with the same in synchronous generators being acted means they just acts as synchronous motors to pump the water back into the upper dam. So that's the major point of considering these storage systems in place. So okay, so our aim is to make the profile of the power consumption profile flat. Since we are from the Indian context, we face two morning peaks and evening peaks, and based on these peaks, we are aiming to minimize those peaks. So for that, we need to take help of the battery energy storage system, because they have the feature of delivering or storing. And another thing is that we all know that the solar, wind, all these works in the MPPT, maximum power point tracking condition. So when is the maximum power point condition for the solar? It's during the afternoon itself. In the afternoon, now in the afternoon we have this curve, but again we have a peak. But and now if we want to close all these generators or the thermal fins, the entire power system scenario that we have, or the load scenario that we have, that can't be taken up by the renewables itself, because although we have 27% of 26% of the solar approximately installed. That is the installed capacity, right? And Out of this 27% installed capacity, at a point of time, we only have around 12 to 13% of the percentage share, instantaneous percentage share of solar. So although we have 27%, but at the present, at any point of time, we can't exceed this value of 12 to 13% of the solar solar generation that participate directly in load sharing. Okay, so although we have a high percentage of generation or installed capacity, we only have half of that value, which can participate each and every time, because the amount of solar energy or the solar insolation is not same all over the country, all over our country, India. So I'm telling about the Indian context. So that means somewhere where we have 900 megawatt or 500 megawatt generating plant, but that generating plant is not giving, because somewhere in Rajasthan we have 50 degrees Celsius at during the afternoon, but somehow or the other, if a plant which is installed somewhere in Assam or somewhere in the eastern side, that won't be getting that much amount of solar insolation. So although it has a maximum, if sun shines at the highest value, highest value in the sense, not sun shines and not in the highest value, if there are no cloud covers and all these things, the insolation value, irradiance is the highest, then we can get a maximum value of 900 megawatt or 500 megawatt, anything we have placed. But since it's not the case, so 27% is placed spread over all over the country, all over our country geographically. But at a point of time, only 12 to 13% of the total power generation is being participated by the solar. So that's a huge difference, and the thermal plants, the importance of the thermal plants are greatly emphasized. Okay, so the okay, so we have the thermal plants also have the capability of inertia. So they have the inertia. So why the inertia is required? Due to the sudden load mismatches, load generation mismatches, the inertia do take a major role. Okay, but that is also absent in case of the renewable. So at that very point of time, that is at the very present context of time, we cannot directly replace the thermal power plants. Okay, so what we can do is that we can use a proper mix of both. And since the MPPT values, MPPT during the MPPTs, that is the maximum power points. So the solar maximum power point occurs during the afternoons, and also the wind also is variable, but most probably we can find it in the evenings or the late nights. Okay, so there is also the load has already shifted. So if we can see that this is a periodic waveform, so it is the midnights, and again peak comes. This curve continues. Okay, so here we have one single cycle, so this cycle again starts. So this is the point where wind is most, and this is the point where solar is most. So these two problem needs to be mitigated somehow, because we have more generation, but no one is means we are absorbing, because but that the amount that is generated, that is exactly not consumed. So what we can do, because we already have the generators in place, na? Because we already have generators in place, we can't shut down all the generators that are delivering the amount of total power, means the thermal generators I saying. So we'll have to keep those generators, because again a evening peak is there. So during those evening peaks, the renewables are uncertain, so the generators, that's the problem. The spinning reserve has grown up much high, spinning reserve value. and that is creating much more problem here. So what we can do is that we can take effective help of the storage system, and that lays the foundation of better storage facilities to be developed. Already we have some storage facilities, but the problem lies is that there are large amount of batteries that are being involved to be a part of the storage systems, and also these batteries uh, will have to be will have to take care of the second life of the battery, because these things are quite challenging when we uh, we look into the bigger picture, because they directly we can't dispose them off, because once the efficiency goes down we can't dispose them off. We'll have to think about their second life, so that creates a problem. So the importance of storage system, that we will be discussing now. What's the importance of the storage system? So as I have already discussed the overview, that again one thing is that we do take the value of these load forecasts. Okay, that we'll discuss later, because it's not becoming out of context. That would become out of context, related not related to the storage part. Okay, so importance, we'll have to mitigate the excess or deficit of the renewables. So excess or deficit. So during the daytime, when there are peak, the batteries are to be discharged, and whenever there are these valleys, then the batteries will be used to store the excess amount of energy. Okay, by renewables. Now, again, another mode of operation that we can see is that islanded. So batteries can help during islanded operation. So what we can see is that during the islanded mode of operation, the since the grid is absent, right? So when the grid is absent, the entire power that is the load entire power that is generated within that island, that power has to be consumed, and also vice versa, the amount of load that is required within that location, within that geographical or within that microgrid, that has to be kept taken up by that has to be met by the renewables in place, the islanded during the islanded mode of operation. So batteries in place. So the batteries are a good option, because they have an ample. If we can store them, that the ideology that I've discussed here, if we can store that amount of energy in these batteries, then we can share them with the customers during the islanded mode of operation, because it would be required, because we'll have to maintain the sync within that entire system. So this is during the islanded mode of operation, the advantage of this, or this importance is can be highly observed. Also, if you flatten the load curve, so this is how the load curves we can flatten that during these. If we consume or store them in the batteries, then that would imply or that would result in a power consumption. So that power consumption ultimately, okay. So when we are consuming the power during these periods, okay. Again also on this side, here we have peaks here. So and here batteries are on, means batteries are absorbing power, so ultimately the power is consumed somehow or the other. Again, during this period, the batteries can deliver power, and ultimately this amount of power that was previously required to be given by the or delivered by the synchronous machines, so we can reduce the generation of the synchronous machine during these periods once these things entirely becomes global strategy all over. So, at least for the Indian context, if these strategies are entirely being taken up, then we can curtail this amount of peak by delivering that excess peak from the excess peak from the batteries or storages, not only batteries. Storages can be pump storage also. We already have the provision, Tehri pump project in West Bengal. Also, we have the Purulia pump project. Okay, so and during this time when the batteries are sorry, when the generation is already being present and suddenly we can do what we can do is that we can use that amount of excess amount of generation to store energy in the battery to again curtail this peak. Okay, so in this way we can maintain at least a flatter profile, means this the positive peaks and negative peaks that can be curtailed. This can be brought down and this can be brought up, and this can be brought down, this can be brought up. So this way continues, so we can flatten the load profiles. Okay, so that's the basic idea, so I've kept here. Now we have non-electric storage, where we have the mechanical storage, electrochemical storage, and we have thermal energy storage. Thermal test, we also thermal energy storage system. Test. Electrochemical, we can consider them in the batteries form. Mechanical, we can consider them as the pump storage flywheels. So already we have discussed what's the function of the pump storage uh, pump storage plants. So during the morning peaks, we can store the excess amount of energy, and during the evening peaks, sorry, not in the morning peaks, during the valleys, we can store the excess amount of energy by uh, pumping the water from the lower dam to the upper dam, and during the evening peaks, evening times, when or evening during the peak period, we can switch on these power plants, so that because the major aim is to maintain, we'll have to maintain the frequency, and these power plants do get a ABT. If you are aware of the term, that is availability based tariffs. So most of these power plants always try to participate in these demand response activities, because for that also they get an extra benefit or availability ABTs. So these ABT means how much they are available, how much, these are the time that are calculated over a period of time, over a month, over a year, over 6 months, quarterly. So based on that they get an extra amount of tariff, and with that extra amount of tariff, that's a kind of motivation for them uh, to you can say to maintain the frequency. So ultimately we have to maintain the frequency within a prescribed band, right? So that band of frequency, mostly it is within 49.85 to 50.05 hertz. So that we'll have to maintain, because otherwise the breaker synchronization won't occur. The breakers won't synchronize. These are generally not followed in the textbooks or like this, but in the practical scenarios where we can greatly observe that the breakers won't synchronize if the frequency of the generation is not within this band, these things, this frequency won't, these circuit breakers won't synchronize. So the major problem is to maintain the frequency, and to maintain the frequency we'll have to always have a faster time response equipment. So as we all know that okay, let me put it here. As we all know that the all these okay, frequency. So based on the stability studies that we perform in the power system, so we what we do is that we Pg minus Pd, based on that is the accelerating power. So initially these are the torques. So these torques are, since the angular speed, based on this angular speed, these torques we have the knowledge, so that these torques are transformed to the power notations, and based on that the stability studies are performed, that if these also we have the h, the acceleration, that is the h is the inertia constant, and we have the pg minus pd, that is the accelerating part. If this value, this p acceleration is positive, that means generation is more, and when generation is more, the rotor would try to accelerate, but all these machines are synchronous machines, so the rotor can't accelerate because the field, we have the field, let's suppose all throughout we have the field windings place, distributed field windings. So we have the distributed field windings in place, and we have the rotor inside. Again, here rotor also has these field windings, rotor bar. It's considered as cylindrical rotor case for the synchronous machine. So when we have this north pole, south pole, four pole machine, let's consider the case for four pole machine also. So what we can observe is that the rotor and the stator, these are the rotor, and also in the stator we have a, here we have a rotor. In this rotor we pass on the DC, and this DC current leads to a flux, and this flux, when this flux cuts this stator side, they produce an EMF, and that, based on that EMF, the current starts flowing, which again this current, the current starts flowing, but this EMF tries to oppose the cause that produced it, that is the Lenz's law. Firstly it's Faraday's law, and then the negative sign is due to the Lenz's law. So Faraday's law and Lenz's law. According to Faraday's law and Lenz's law, it tries to follow the cause, and now the rotor and the stator, they, here's the north pole, so here the south pole, they lock with each other, and once they are locked, that entire locking position, this lock is considered is same for all the other sections also. So now it starts rotating. So when it starts rotating, this entire rotation that we can see, that it starts rotating, we can see that here we have discussed that there is a positive or a negative. If PD is high, then we will have a negative. So now these are, see, this machine is synchronous machine, so the positive and negative acceleration won't disturb this sync, but what it will do is that if these two, the rotor field and the stator field, if both of them are in exact this, the central point and its central point passes to the same axis, then then this condition is for the rotor angle 0. But during these positive or negative push or power mismatches, this rotor would start swinging, and that swing already, this is in practical cases, this isn't in zero value, it's somewhere in around 10, 15, 30 degrees, within 30 degrees. But in case of uh, shift, means positive or negative acceleration, this value shifts, and that leads to the rotor swings, and that's the reason why it is also known as swing equation. The rotor starts swinging, but the locking becomes tries to become looser, weaker. But if the value or the stability value that we all know from the equal area criteria, if it doesn't cross the del max value, then let's say it's del 0, after swing it's del 1, and del max we have, that is 180 minus del 1. So if that value doesn't cross that upper, because here what we can see, this is the rotor starts swinging from this point to this point, means up to this point it can reach, but once this point is reached, and after if it goes anywhere just beyond that point, the entire system becomes unstable. And once the system becomes unstable, this locking is no more prevalent, and after that the rotor rotor lock stator locking is disconnected, and accordingly the synchronous machine gets switched off, because means the breaker gets initially switched off, because the machine, the frequency can't be maintained if the synchronism breaks. So that's the main problem, that we'll have to maintain the frequency within that predefined range, and that can be maintained only by using various kinds of storage technologies, because the inertia is main issue of inertia is absent. And that's the reason that the storage facilities needs to be properly designed and deployed to deliver a faster or better, uh, we can say a better smart grid operation, we can say. Okay. So in the mechanical part, we have the pump storage based compressed air storage, and flywheel based. Okay. And in the electrochemical based, we have the batteries. Okay. The batteries, hydrogen systems, and thermal systems, thermal energy storage systems. We can, in the form of hot water, chiller, and all these things, we can uh, make in place. So superconducting materials, so all these things. So battery energy storage system, the advantages is that it the reliability is much more increased for the with the implement. Okay. Then also, as we have already discussed, that the power mismatches can be met, so the power balance power balance can be power balance can be maintained. Okay. Then we can see that system losses can be minimized, because we are operating them in a much better way, because the smart grid operation is aiming, or or we can say that the smart grid operation is delivering results in a much better way, and that leads to the option of, what we can say that overall losses reduction, and that is resulting in a efficiency improvement. Okay. So so uh, we can flatten the load curve, as per, and also some ancillary services. ancillary services. So now we'll have to find out that the batteries that we are trying to design, these will also have to have some features, that these battery energy storage systems should have some features associated with them, and these features can be in the form of the power system, means they are batteries which are trying to, you can say, they are trying to they will be implemented in the power system. So for that we will have to design the batteries based on certain criteria, certain features, that so as to meet the power system demand. So first of all we'll have to meet the power system requirements, the criterias, that these amount of power system, these are the foundations, these are the what we can say, rules or guidelines that we need to follow. Okay, then storage capacity should be predefined, storage capacity. Okay, also we can also say that the amount of these batteries, what we can, how for how long it's storage, uh, it can be segmented into two part, that storage capacity, or we can say storage tenure, means how long it can take the, or it can maintain that amount of uh, storage time, means how long it can store that amount of energy and dissipate accordingly. So it has to be efficient, right? Also we can also say that the battery's energy density, the lifetime of the battery, these things to be proper, are to be properly designed, the charging or discharging rates, etc. Okay, so based on that, we have some various terminologies, that is the duty cycle of the battery. So what are the duty cycle? So the amount which is expected from the battery to deliver that much amount of energy, means the amount of time for which, or the amount of energy that is expected to be supplied by the battery. Okay, for the specified time periods. So again we have the cell size, how much should be the cell size. We also have the equalizing charge. So so there are some uh, characteristics or the terminologies that needs to be followed. Now we have the type of batteries. So there are various type of batteries, like lead acid batteries, like sodium sulfur batteries. We have nickel cadmium NiCd. We have nickel metal hydride. Also we have lithium ion, which is lithium ion, or we have lithium ion polymer. You can get this in the slides itself. So these are the types of batteries. We have some of the types of batteries, maybe more, but so for that we also need to find out the some terminologies, that SOC, state of charge. So SOC is we can find out that which amount of charge that is left in the battery. So using this SOC value, the EVs that we can see, all these EVs, we what we finally see is the SOC value, state of charge. So these state of charge values, based on the state of charge, how longer the battery can continue, how long the battery can continue after this time, after this period of time, that we can observe from the state of charge. Okay. Again, we have the depth of discharge DOD, and it is 1 minus SOC. So if the SOC is in percentage, and this is also a percentage, so there are values that the SOC values should be kept. There are ranges, but it can go from 0 to 100. But in practical cases, this is the ideal case. But in practical cases, it is varied from 50 to 90. But beyond below 20, it's not taken, because that would disturb the battery life of these of the battery life. Okay. So some governing equations we can also observe that. So SOC is initial SOC to 0th condition by plus 1 by 0 to G dt, where this is the initial SOC, this is the capacitor, means this is the, we have the characteristics, how the charging characteristics. There we have battery modeling. So this is the model. We can see that I in the V, so charging discharging resistance, and based on this we can see that the how the state of charge relation is dependent. So also we have the superconducting magnetic energy storage system, which is also known as SMES. Okay, SMES. In SMES, it is the most related to AGCs. Also, we have the spinning reserves. Also, we have the power backups and VAR control. Also, we have the power factor control, etc. So that's the part of SMES, superconducting magnetic energy storage system. So ultra capacitors, supercapacitors, have the idea that how these supercapacitors and ultra capacitors are designed. Okay, so they can also store energy, and they can be used in DC microgrids to uh, face when switching transients are being faced, because fault right through conditions that is faced by the DFIGs. Okay, etc., like voltage stabilizing activities. So these are the overall idea of how these storage systems like the supercapacitors, uh, batteries, types of batteries, how they are dependent. So there are factors which also affects the type of, means factors which affects the life of the battery. So battery performance. So first we all know that battery temperature. Battery temperature is when we have temperature can be high or low. So if it is low, then the discharge temperature will result in reduction of capacity. Reduction. And again, high temperatures ampere hour capacity increases. So there has to be a trade-off. So also you have the service life. Service life, we all know that the discharge currents, the discharge current affects the service life. So based on the discharge current, the hours of service do get hampered. Also, we have the type of discharge. Also, we have voltage regulation. Again, we have the charging voltage scenarios. Also, we have the storage conditions. Again, we have age of the batteries. So ultimately, what we can observe that there are lot many factors which affects the life of the batteries, design aspects. So overall, there are some number of based on the IEEE standards, as IEEE standards are mostly followed while deploying these systems or designing these systems. IEEE standards, and that the standard is followed because they're based on the trust of these easier delivery of these proposals from these IEEE side. What we can see that battery sizing is dependent upon various factors. Okay, and it is margin, design margin, age. Also, we have the cells. We have the initial capacity. So these things needs to be taken care of while designing these battery storage systems. So okay, so why we are transforming towards the microgrids, DC microgrids, that we can discuss a bit. That. So here we can observe that these are the data centers. This is a DC bus. So all throughout we are discussing about the AC section, but from the microgrid point of view, what we can observe that we have a huge number of loads that are operated in DC, right? So out of these huge number of loads, we can see that these loads are being operated mostly on DCs, like loads, uh, in the evening side, evening peaks, evening time, we can see or observe that a lot of storage systems are being, that we have discussed, that these things are to be deployed, but the loads are also DC. So what we can do is that already we have some loads are also AC, but mostly light loads are DC. So we can directly use, if we can directly use that DC load, okay, that would greatly reduce our cost because converter costs are involved, okay. And the advantage is that the photovoltaic cells, PV generate in DC. Fuel cell we have DC. Wind we have AC. For this we need to convert, but battery we again have DC. Supercapacitor we again have DC. So out of these five types, we can observe that loads, and loads also lighting loads, these loads, heating loads, communication towers, data centers, all these loads are also DC. So if you can directly use the DC to deliver these DC loads, that would reduce the transmission cost or the conversion cost, because uh, transmission, in the transmission side for the AC transmission, we, at least if it is in the distribution side, the distribution, if we can consider, for the distribution also we need to have three-phase line, and we all know that in the three-phase line, if we want to distribute, they'll have to have three phases, one neutral. Okay, but in case of DC, we can directly send, only two lines are required, positive and negative. And also if the ground is positive, there are provision negatives over it and ground. So these are used in mostly flat, but let's take consider the case for the positive and negative only. Again, in case of converters, so converter cost greatly reduces, okay. So also there are synchronization is much easy, because in AC we have the problem of AC, sorry, frequency that has to come within that range, and only that after that the things would synchronize, otherwise that won't synchronize. So no problem of the harmonics in case of DC. So there are a lot many advantages, no issue of harmonics, okay. Again, if we can say that uh, eddy current and hysteresis losses are absent. So we get to see a lot many advantages, right? So if we can do one thing, we can directly communicate in DC. That would lead to DC microgrid. Okay, and we also know that we have, if the communication cost is that not communication, that is also we can say the distribution cost. So there can be there can be DC operation based on some voltage level, HVDC, where we get to see 500 kV DC, ANV MVDC, where we get to see 11 kV to 33 kV DC, and we have LVDC where we get to see the 348 volt, 380 volt, 600 volt DC. Okay, so ultimately it reduces the reliability, reduces the dependency on the main grid, and hence the reliability of the entire operation can be obtained. And in the villages, in the areas where the power consumption is mostly limited, there we can definitely implant these techniques so that easier mode of operation can be easier mode of some costs can definitely be reduced because they are in-house and they can be directly utilized there itself. Okay? And the things can directly connect to the DC bus equipments because in between the what we have in between, that is the AC/DC and DC/AC, sorry, AC to DC conversion phases. But these DC loads, if we have first DC to AC, and if the bus was AC, then for these DC loads we need to convert DC to AC and again AC to DC to feed these DC loads. But here we can directly feed them. So the control actions have become much more flexible as well, and the applications what we can see can be done at a much lower voltage levels operates. Also we can see that the bipolar link, DC bipolar links can be used. There can be multi-bus topologies that can be framed, dual bus which we can separately feed the microgrid. Okay, so reconfigurable topologies like DC ring bus architecture. So here's one of the architecture that is shown here. So DC ring bus. Also we have the multi-terminal DC. So here it is, we can see the DC ring bus architecture where we have a diesel generator connected here which is converting DC-DC, AC-DC conversion. Load is also there, but PV array is producing DC-DC. And fuel cell also DC-DC, battery DC-DC conversion, PV array. And from the grid or utility side, this is the AC-DC. So we can see that the circuit breakers are associated with the intelligent electronic devices. These are the breakers, these are breakers. This is the DC bus arrangement. We can see the entire path is closed Okay. Also, we get to see the IV characteristics where the MPPT value, the things are operated at the MPPT because this is the voltage and the current values. If we multiply them, the point this is the point where we obtain the P max because this is the current value max and this is the voltage value max. So V max and the I max delivers P max. So this is the PV cell modeling part. How the PV cell model needs to be done, and based on there are some ideal cases and as well, and we can observe that the generic model. This is the generic model of the PV cell. Previously also we have discussed this is the series resistor, this is the parallel resistor, this is the current, this is the VI. So, diode, sorry. So this is the diagram. Okay. So we can see some challenges in okay. Okay. So these are the challenges. Challenges we can observe in the DC microgrids. Uh, so lack of standards, protection issues, no DC circuit breaker uh, that is yet to be updated or obtained. So lack of DC infrastructure, circulating currents in parallel, grounding issues, unable to feed AC loads of industries, commercial and residential applications. So there are AC loads, not only DC loads are there. So there has to be a mix and match, and things needs to be handled properly. And higher power losses in LVDC distribution networks. Okay, so some types of loads that we also need to be at least have some overview that constant current loads, constant voltage, constant impedance. Altogether, if also there are loading scenarios which is a mix of ZIP model, which is, and also the other part in Indian context, mostly the loads are induction motor loads. And in these induction motor loads, about 60 to 70% of Indian loading scenario is induction motor loads. Now in these induction motor loads, we can observe that the problem of these induction motor loads is that they have total reverse recovery feature or characteristics, and accordingly what we can see is that uh, if suppose in the load flow studies we can see that we generally take okay, am I not audible? Hello, hello. Okay, am I audible? Am I audible?
Yeah, yeah, audible, audible.
Okay, 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 thank you. So in the load flow studies that we generally take into consideration that since the loading scenarios are highly dependent, so in the load flow studies we generally take care of the values of P and Q, and mostly they are taken to be constant load models, constant values. But here we are also seeing that the loads are the current and voltage or impedance type of load. But in case of load flow studies we generally take, this was the problem that was I trying to say some days back, that constant, due to this constant feature we generally take the value. But we need to know that uh, why these values are taken as constant, because with the voltage dips the value of this induction motor has the feature of reverse recovery characteristics, reverse recovery. So based on this reverse recovery, although there is a dip, comparatively it will also face a dip for a small time, but it will again come back to its original power level uh, by acquiring with that amount of voltage means. So for that point of time we can see that mostly the loads are governed by the induction machine loads, and also we will have to take care of the value that we can say that somehow or the other we'll have to take these things into consideration, that how the load modeling would impact the, we can get to know that these load models are highly means the precision of this load model would also impact the type of distribution system operation or microgrid operation, and how these production equipments, how these microgrid models are to be developed. So on an average we can see that there can be variable speed drives also, 40 to 20, uh, means there are temperature transducers being present. So examples means you have the constant current load, we can see that uh, temperature transducers, also for the constant voltage type loads we have speed drives, or that is the induction motor that I've discussed. And also for the constant impedance load we have the incandescent bulbs. Okay, so overall we have to have a good load model, and for that the converter models are to be properly developed, and accordingly the outcomes are obtained to properly enact in the AC microgrid system or DC microgrid system. But for the time being, since we are focusing on DC, but the AC can't be overlooked because that's the main type of system. Although we are trying to at least take the advantage of the DC part, because various loads are present in the DC as well. So that's the thing, and some islanding. So there are also applications for the DC types, like the traction is also a part of DC that we need to always keep in mind. Also some the huge data centers, then EV charging stations, okay, communication towers, etc. So we have discussed about the challenges of the microgrids and some basic islanding detection techniques that we why the islanding operation is required. So here DG control, synchronous generator control, inverter based control, and with that the grid connected mode of operation and grid feeding strategy, grid supporting strategy. With the islanding mode we have grid forming, grid feeding and grid supporting mode of operation. So these are the parts of AC microgrid in operation. So the normal mode of operation, which is grid connected mode of operation. Also we have the isolated mode of operation or islanding mode of operation. Also we have the islanding operation. It is more critical because the standards are not well developed. So for that the a large number of test cases needs to be solved initially, and that after that we can dive directly in various kinds of, because the safety concern is quite high, because the 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 personals who are involved in these island in these DG controls in these microgrids, they need to have that data point that yes, these kinds of actions might occur, but in practical cases there can be scenarios where these things might not pop up. In practical scenarios, someday or the other it would suddenly pop up and the entire things would go in disruption, right? So based on that, some active and passive islanding techniques are also developed, so that in the next week's lecture some support system, ancillary support, all these things that would be discussed in the next day. So for this weeks we can discuss some questions. Uh, let me just put up the answer. So, okay, we shall start, but before that, so yours is the question that if the fault current seen by the IVDR, if the fault current seen by the relay, sorry, fault current seen by the relay is due to the contribution of only IVDR, then what would be del IVDF, sorry, del IVF, that is the positive sequence component. So what would be the positive sequence component? So there were two parts where the IVDRs and SBDRs. So IVDRs had value of 2 pu, SBDRs had value of 5 pu. So we need to have a, because for these two cases relay design had to be made quite different for these two cases individually. So what uh, control strategies were formulated to calculate the impact factor, and accordingly the for the IBDS, what followed by the IBDS. So IBDRs have low value. So for that, this should be made high numerator, and for SBDR it should be made low value. So this is numerator should be low so that the impact factor becomes small. So here we can see, yes, 1F 2F into del IF. So this is the del IF. Okay, this is the del IF. That del IF can be calculated. This is for the IBDR. This is for the SBDR. So the SBDR it's minus. So IBDR it's plus. Okay. So the answer of this question is C. And the lower and upper limit for the TDS time delay settings are set to which value? Lower and upper limit. It is 0.505 to 1. This is at the lower and upper limits of the TDS. So the polarizing quantity in the superimposed positive sequence method of fault detection or superimposed positive detection method of fault direction method of fault direction detection is, what is the polarizing quantity? So we have the polarizing quantity and we have the actuating quantity. So here we are asked to mark the polarizing quantity. Based on which the angles are calculated. So here we can see here VE is the polarizing quantity. So what is VE? VE is the pre-fault voltage. Okay, pre-fault voltage. So again, a relay's plug setting can be altered by changing relay's plug setting. We need to change the value of plug setting because sometimes or the other uh, values don't show up within this within some range, because there are some general values which we can calculate, but uh, still relays don't if the relay don't show up, we need to change the values based on the location also. We need to change the values. So what needs to be altered? It's the number of ampere turns. Okay. In a static overcurrent relay, inverse time characteristics are obtained by transistor amplifier, integrating circuit, transistor switch, differentiator circuit. Inverse time characteristics. We have a transistor amplifier, integrating circuit, transistor circuit, and differentiator circuit. Differentiator circuit. Differentiating circuit. It is an integrating circuit. Okay. Okay. In which mode of operation the fault current in the microgrid is high? Islanding mode of operation, grid connected mode of operation. We have the grid connected mode grid here. All the things are inside. It is a grid. Yes. So in which mode of operation we have the loads? Yeah. So if fault occurs, if the grid is not present, the current value would be low. If it is present, definitely the current value would be high. Again, due to the bidirectional fault, which types of traditional relays are unable to provide relay safety protection? Due to bidirectional fault, which types of traditional relays unable to provide safety protection? It is unidirectional overcurrent relay. In which while estimating the fault direction using superimposed currents, the sign of del phi during the reverse fault when power flowing is in upstream. So that's the rule. The rule we'll have to follow is that power flowing in upstream direction. So what would be the sign of phi? It would be positive. In the two bus system, the load is drawing 200 amp current from one bus from bus 1 to bus 2. After the fault, the current at one bus is increased to 1500. Then the superimposed current becomes in the two bus system, the load is drawing the 200 ampere current from bus 1 to bus 2. After fault, after fault, the current at bus 1 is increased to 1500. Then find the superimposed current at bus 1. So it becomes 1300. The converters used for battery, PV, ultracapacitor, PMSG, DC microgrid respectively are: battery is bidirectional, PV is unidirectional, ultracapacitor is again bidirectional, PMSG, permanent synchronous generator, is unidirectional. So A is correct. Which of the following inverters may not be suitable for grid connected mode? It is grid forming converters. Okay. Grid feeding converters are connected to the grid in dash to inject power to an energized utility system. Connected in parallel with high impedance values. Which of the following battery is suitable for laptops and electric vehicle applications? We can see in our daily life which batteries are suitable for laptops and electric vehicle applications. Lithium ion batteries. Which of the following modes of voltage source converters is suitable for both islanded and grid connected scenarios? Both island voltage source converters, islanded and grid connected, both should be taken care of. It is being done by grid supporting mode. Which of these is not the microgrid ancillary service during the grid connected mode? Congestion management, improving power quality, black start, frequency control support, etc. Out of four, not the microgrid ancillary service during grid connected mode. Already it's connected to grid, so answer is black start. So with this we are done for the day, and if you have any questions then we can discuss, otherwise we will meet again on the next day. Thank you. So you can leave for today.